Welcome to Workshop 7. This is the workshop for the previous two lectures on chemical reactivity, as well as our introduction to mechanism. So we have a few problems for each lecture. Let's go ahead and start with this first problem dealing with chemical reactivity. We have this chemical reaction. I'll put it in a box here, where we start with this bromine containing alcohol here, and it starts as a chain, but it seems to close into a ring system and expel HBr. Okay, so we have some questions that we want to answer here. The first question down here, A, says estimate the delta H, the change in enthalpy, for the reaction using the values given. So we have the delta H's for the different bonds that are being broken and being formed here. The CBr bond we're breaking, this is about 285 kilojoules per mole. The OH bond is about 498 kilojoules per mole. We're forming a CO bond. If we look here, we're forming a CO bond in the ring system. That's 381. And we're also forming HBr as a byproduct. The HBr bond is also being formed. That's 368 kilojoules per mole. So how do we estimate the delta H for the reaction here? Well, remember, when we break a chemical bond, we need to input energy. Remember, it's like picking up a stick and breaking it. You need to use energy to break that stick. We need energy to break that bond. So it requires energy to do that. So these are going to be positive values here for the broken bonds. And when we're forming bonds, we release heat. When a bond is formed, it releases heat. So this is going to be negative values when we release heat to the environment. When we release heat, that's going to be for the bonds formed. So the bonds broken will be positive values. The bonds formed will be negative values. And we simply sum all of these together. So we'll have positive 285. And we have positive 498, and we have negative 381, and we have negative 368. So if we sum all these together, then we should get positive 34 kilojoules per mole. Positive 34 kilojoules per mole is approximately the delta H for the reaction. What does a positive delta H mean? Well, remember, delta H is the enthalpy change. This is going to determine if a reaction is exothermic or endothermic. So if a reaction is positive, that means it's going to be an endothermic reaction. Okay, so we have positive 34 kilojoules per mole. This is an endothermic reaction. What about delta S? That's the entropy. Now, let me draw up top the equation we should remember, the big one. Delta G equals delta H minus T delta S. This is the Gibbs free energy. We have our enthalpy part of the equation, the delta H, and we have the entropy part of the equation, T delta S. Okay. So now this question is regarding the delta S, the entropy. It says delta S entropy is positive. Why? Well, let's consider what gives us positive or negative entropy. Remember, we have two different ways we can consider entropy for a chemical reaction like this. Entropy could increase if we go from A, B, breaking apart into A plus B, right? If we break one thing into multiple parts, that's an increase in entropy. We can also increase entropy when we go from a ring system breaking apart into a straight chain system. 1, 2, 3, 4, 5, 6. So if we break apart this 6-membered ring into a 6-membered chain, we would be increasing entropy. Remember, entropy is a measure of randomness or disorder. So if we break apart one component into multiple components, we're increasing entropy. And if we are breaking apart this ring system, we are increasing entropy because we now have many more different conformations that can be adopted by this system. We're almost breaking it apart halfway. So breaking things apart into its components is going to increase entropy. Now we have both of these processes occurring above, right? In this reaction, we have a straight chain system. We have a straight chain system becoming a ring system, right? So if we have this chain system becoming a ring system, that is going to lower the entropy. Let me draw it like this. I'll draw it with text here. So the chain becoming a ring means lower entropy. Okay, the chain becoming a ring means lower entropy. But we also have the chain breaking apart into two different things, right? We have this oxygen-containing ring, and we also have HBr. So we're breaking one molecule into two molecules. So breaking the molecule into two parts increases entropy. So now it's simply a matter of which one affects it more. So if delta S is positive and the chain is becoming a ring, which lowers entropy, the molecule is breaking apart into two parts, which increases entropy, that means that this is simply having more of an effect on the overall system. The molecule breaking apart into two different parts, increasing entropy, is having a stronger effect on the system. So this is going to give us a positive change in entropy, an increase in entropy. Sure, the chain becoming a ring will lower the entropy, of course, but the breaking apart into two different molecules is clearly having a stronger effect if the delta S is positive. Okay. Part C, determine the sign of delta G. How do we determine the sign of delta G? Well, let's look up at our equation here. If we have delta G equals delta H minus T delta S, how can we use that to determine the sign of delta G? Okay, so delta G. Now for delta H, we had positive 34. I'm not even going to put 34. I'm just going to put a positive number for delta H minus T delta S minus T delta S. Now temperature is always positive because it's in Kelvin. Okay, so temperature is always positive. And from part B, we see that S is always positive. Okay, so what we have here is delta G is equal to a positive number minus a positive number times a positive number. Okay, so ultimately what we have is delta G is equal to a positive number minus a positive number. What does that mean for the sign of delta G? Well, a positive minus a positive is going to be a negative unless temperature is low, then it could still be a positive, right? If we have a large number minus a small number, it could stay positive. Otherwise, delta G will be negative. So let's write that out here. Delta G would be negative unless temperature was low. Then it would stay positive. Okay, so that would be our answer for part C. Delta G would be negative. Unless temperature was low, then it could be positive, because what we have is a positive minus a positive. So a positive minus a positive could be a negative, but a positive minus a positive could also be a positive number. At low temperatures, it's more likely that this delta G is going to stay positive because we will have a smaller number that we're subtracting. Okay? So delta G would be negative unless temperature was low. Unless temperature was a small number, then it would stay positive. Does delta G, part D here, does delta G depend on temperature? As we just discussed, yes. Delta G does depend on temperature. At high temperature, it would be a negative delta G, and at low temperature, it would be a positive delta G. Is the magnitude of delta G dependent on temperature? The magnitude meaning the size of delta G dependent on T? Yes, again, the magnitude of delta G is dependent on T because we are subtracting minus T delta S. So this is clearly a value here, okay? So if T is very high, then we are going to have a large number there, and that's going to affect our magnitude of delta G. So temperature has an effect on both the spontaneity of a reaction, the sign of delta G, as well as the magnitude of delta G. Okay. Remember, delta G has nothing to do with the rate of a reaction. Delta G is only the spontaneity of a reaction. Okay. Very key distinction there. Okay, so let's quickly go through all these answers. So delta H, we said, was plus 34 kilojoules per mole. Delta S is positive. Why? Because we're breaking apart. A, B is being broken apart into A plus B, breaking apart into two different things. Determine the sign of delta G. We said right over here, this would be, I'll put a little star. Star, here's our answer for part C. Delta G would be negative. Unless temperature was low, then it would stay positive. Does delta G depend on temperature? The sign, yes. Is the magnitude also dependent? Yes. The magnitude and the sign of delta G are dependent on the temperature. Okay. Again, Gibbs free energy, very important equation, so make sure you know that for this chapter. Okay, delta G equals delta H minus T delta S. So for this problem here, we're given three different reactions. 1, 2, 3. I'll put A, B, and C. And now for each of these, we are going to determine the entropy change for each reaction. So we're looking at change in entropy delta S. Okay. The change in entropy of the reaction could also see as delta S of the system, right? So we're looking at the change in entropy of the system, okay? Delta S for the reaction or delta S for the system. What's the change in entropy for each reaction? So remember what we talked about on the last problem here. When we consider entropy in chemistry, we are considering a molecule breaking apart into more components or a ring system breaking apart into a chain, right? That's going to be increasing entropy. So looking at our first reaction here, A, we have a ring system plus HBr. We still have a ring system, so that ring system is not being broken apart, but we are combining that HBr with the ring system. So we're combining two components into one. So this is going to be lowering the entropy. So this would be a negative value for entropy. If we are taking two components and combining them into one, that's a decrease, a lowering in entropy. So that would give us a negative value for entropy. For B, we have two components turning into two different components. So if we start with two components and we end up with two components, we aren't forming or breaking any sort of ring system. Starting with two, ending with two, that would be a net zero change in entropy. Okay, there's no change in entropy there. For part C, we have one component and we are breaking it apart into two components, right? This is called an elimination reaction, which we'll discuss very shortly. We're forming a double bond and kicking off that chlorine. We're forming HCl from this. Either way, we're starting with one molecule and we're ending with two molecules. This would be a positive change in entropy because we are breaking the molecule apart into components. And remember, when you break something apart into its components, that is an increase in entropy. Okay? Again, if we have a ring system and we break apart that ring system, that would also be an increase in entropy. Okay, so those are the two things that we want to look out for when we consider entropy in organic chemistry. So for this question, we are asked to rank the following carbocations in terms of their stability. So remember what we discussed in the previous lecture where we talked about hyperconjugation stabilizing carbocations. Remember, tertiary carbocations are the most stable, secondary, followed by primary, followed by a simple methyl carbocation. So those tertiary carbocations are the most stable, the methyl are the least stable. And remember that stability is due to hyperconjugation stabilizing that positive charge. Those neighboring bonds sort of stabilize that positive charge. Okay, so looking at A, we have three different carbocations to compare. And this one should be pretty straightforward. It's simply comparing primary, secondary, and tertiary carbocations. We have a tertiary carbocation here. This would be a tertiary carbocation. This is a primary carbocation. It's only connected to one other carbon. And this is a secondary carbocation because it's connected to two other carbons. So the most stable is going to be this one here. We'll put a 1 there for most stable. The secondary is the next most stable, so we'll put a 2. And then the primary is the third most stable, so we'll put a 3 there. We'll rank them 1, 2, 3 in terms of stability. Okay. Tertiary most stable, primary least stable. Okay, now for B, we have something similar. We have a primary carbocation here. We have a secondary carbocation here. And we have a secondary carbocation here. Okay, so interesting. So the primary is going to be our least stable. Obviously, that primary will be number 3. That's the least stable. But which of the two secondary carbocations are more stable? Which one is more stable? Now, in order to answer this question, we need to remember a very important word in organic chemistry, and that's resonance. We need to remember resonance. Resonance will be in almost every chapter to some degree, and it's very important in organic chemistry. Which one of these two structures on the bottom right can partake in resonance? Well, this one over here on the far right can partake in resonance because we have a positive charge adjacent to double bonds in the allylic position. So because we have these double bonds in conjugation with this positive charge here, we could draw resonance structures where we move those pi bonds around and we draw those resonance structures. Either way, this positive charge, which remember, positive charge is innately unstable. It wants to be stabilized. Resonance is a stabilizing force. So if that positive charge is partaking in resonance, that's a net stabilization. So that secondary carbocation is more stable because that carbocation is stabilized through resonance. The central one here is not stabilized through resonance because we have this sp3 hybridized carbon in the way. So the positive charge is isolated from these double bonds and there's no resonance occurring. Okay? So this one on the right, on the box here, is the most stable. We'll put a 1 there. It's the most stable, followed by 2, followed by 3, the primary carbocation. And again, this secondary carbocation is more stable because it is resonance stabilized. So make sure you look out for those resonance stabilization effects. Okay? Okay, so now we're going to spend some time on the mechanism part, which is the more important part. The mechanism and understanding mechanisms is very important for organic chemistry. So we'll spend most of the time in this workshop working on these mechanisms. So let's look at this mechanism I just drew out here. Obviously, it looks like a lot when you first consider organic mechanisms, but let's take each step one at a time. All the arrows are already drawn. We're just going to talk about the arrows and label each mechanistic step for this process, okay? Remember, R just stands for some generic carbon-containing group. Could be anything. We just call it R, okay? So we have some carbon-containing group R attached to a carbonyl, and on that carbonyl is chlorine, okay? So what happens in this first step? Well, we have another R, and this R has a lone pair to negative charge, which should be a good, what? Nucleophile or electrophile? This should be a good nucleophile. Remember, nucleophiles typically have a lone pair, a negative or a partial negative on them, and they can form a new bond, okay? Those nucleophiles are going to go out and make a new bond, okay? So if you see a lone pair with a negative charge, that's likely going to be a good nucleophile. So this R minus, this lone pair, is doing a nucleophilic attack. Okay, it's making a bond. Remember, the base of a carbonyl is quite reactive to nucleophiles. That oxygen is partially positive, and that carbon is partially, the oxygen is partially negative, and the carbon is partially positive. Okay, so the base of a carbonyl is a fairly good electrophile, and we're going to see it quite often. Okay, so the nucleophile attacks the electrophile, makes a bond with this carbon, and remember, when this process happens to a carbonyl, the pi bond is kicked up to be a lone pair because we need to make space for that new bond. That carbon can only hold 4 bonds at a time. So if a nucleophile comes in and makes a new bond, the pi bond is kicked out. It's kicked up to be a lone pair instead, okay? That gives us this product over here, okay, the second product shown. Now, these arrows here, well, let's label this, of course. What would this step be called? This would be called nucleophilic attack. Okay, so we have nucleophilic attack. That's step number 1. Now, what happens in step number 2, if we look here around where I boxed in, what's happening between these two products? Okay, we have 2 R's, we have 2 R's, we have an oxygen, we have an oxygen, but it looks like the chlorine is leaving. The chlorine is no longer there. So what is that? That's likely going to be loss of a leaving group. Loss of a leaving group. Now let's consider the mechanistic arrows for this loss of a leaving group. Okay. Now the chlorine is leaving, so we're familiar with this lower arrow here, right? This chlorine is leaving and it's taking its electrons with it. Okay. That's the arrow we usually see. Now on carbonyls, or when we have an adjacent atom with lone pairs, we can get this extra little arrow here, which is called internal assistance. internal assistance. That's this little arrow right here. I'm going to draw a blue arrow to it. Internal assistance. That's, oh, let me get blue. That's this little extra arrow right here. Okay. So internal assistance is just when you have a neighboring atom, typically with a lone pair like this, and this lone pair can come down to form a pi bond and sort of help kick off that leaving group, okay? Because if we look at the product here, we see a C double bond O. That double bond has reformed. And that double bond reforms in the same step that the leaving group leaves. So sure, leaving groups can leave spontaneously, okay, that can happen. But when we have lone pairs next door, then we have this extra little arrow here where the lone pair can come down and kick off that leaving group through internal assistance. That's what we call that, okay? Internal assistance. So when that happens, we form that C double bond O, okay? So that's loss of a leaving group. Now we are left with this ketone, this simple ketone. And again, we get a nucleophilic attack. Just as before, R minus comes in, nucleophilic attack. This R minus comes in, attacks the carbonyl, okay? So here's our arrow, attacks the base of the carbonyl, and kicks up the pi bond to be a lone pair on oxygen. So again, we get this tetrahedral complex here. Now we have 3 R's connected to that carbon, as well as 1 O minus. Now for the final step here, if we compare this to the final product, the only difference is a hydrogen. So what's happening here? This oxygen is grabbing a hydrogen, taking that hydrogen. The electrons are being left behind, of course. So this is called what? This is a proton transfer. We are transferring ownership of a proton, H+, from one molecule to another. And again, let's walk through the arrow here. I'll highlight in red here just so we can see. This lone pair here, it could be any lone pair, I'm just picking one of them. This red lone pair is reaching out and it's grabbing this proton, okay? It's making a bond to that hydrogen, and the hydrogen is leaving behind its electrons with oxygen. So only the proton is coming, not the electrons. The electrons are staying behind. Make sure you remember that part of the proton transfer, okay? So the oxygen is grabbing the proton, leaving behind its electrons. So that hydrogen, let's highlight it in green. That green hydrogen starts out here and ends up on our final product here. So that would be a proton transfer. Okay, so going through the whole mechanism one more time, we start with this. This is called an acyl chloride. It is attacked, nucleophilic attack to the carbonyl. The electrons are kicked up. Internal assistance helps the leaving group leave. The chlorine leaves, reforming the carbonyl. The carbonyl is then attacked once again, nucleophilic attack with R minus. That gives us this tetrahedral complex here, which is finally protonated through a proton transfer reaction to give us an alcohol instead of an oxide. So the O minus is protonated to give us the alcohol. So we end up with a tertiary alcohol with 3 R groups attached to it. Okay, so that's a good walkthrough of a general mechanism. Hopefully we're starting to develop some of the language that comes along with it. It can almost be like learning a whole nother language, speaking in organic chemistry. But the more problems you solve, the easier it will become. Okay. So for the next few problems, we are going to work on drawing the mechanistic arrows. Okay, so let's take a look at those arrows. So for this problem here, it probably looks like a nightmare to look at this. There's a lot going on, and it can be very complicated. But we're going to go through this step by step and simply draw mechanistic arrows for each step. Now for each step, we're given the reagent that we need, and we're also shown the product. So it should be very easy to draw each mechanistic step if we can see the product, okay? So just looking at the first two right here in the box, okay? Just looking at that and ignoring everything else, what happens in the very first step? It looks like one of the carbonyls is gaining a hydrogen, right? We're protonating one of the carbonyls. So what is this going to be? This is going to be a proton transfer reaction. So let's transfer a proton. Let's take a lone pair on this oxygen, grab a proton, and leave behind its electrons. Okay, maybe I'll do it in blue so it stands out a little more in this nightmare. Okay, the blue arrow, that's showing the electrons on the oxygen grabbing the hydrogen, and the electrons are being left behind on oxygen. That's a proton transfer. Okay, so that's all we have to do for the first one. Now for the second step of the reaction, what's going on here, if we just consider what's going on in the blue box here, what's going on in the second step? It looks like a nucleophilic attack because we have this water molecule above the arrows and it's making a bond with this carbon, right? We see this water molecule here is making a bond with the carbonyl. So let's draw a nucleophilic attack. Let's take a lone pair on water and attack the carbonyl. So here's our nucleophile, this lone pair on water, and then our electrophile is the base of the carbonyl. Okay, remember the base of the carbonyl is going to be one of our most common electrophiles. So the nucleophile attacks the electrophile. And what happens when we attack the base of a carbonyl with a nucleophile? We kick up the pi bond to be a lone pair because we need to make space for that bond to form. This carbon can't make 5 bonds. It can only have 4 bonds at a time. So if it's attacked, the pi bond is kicked up out of the way and it becomes a lone pair. Okay. So just for fun here, I'll highlight this green oxygen here. This green oxygen is now this one right here. That green oxygen is now that one. It becomes OH. And this water molecule, let's put this one as this pink color here. This oxygen here is making a bond with that carbon. It has 2 hydrogens on it. That's this one right here, OH2+. Okay? So that pink oxygen comes in and attacks the base of the carbonyl. That's a nucleophilic attack. And it makes a bond with that carbon. So now both the pink and the green oxygens are bonded to the same carbon. This pink oxygen has an extra H on it, okay? So what we have to do is we have to get rid of it via proton transfer. That should be the next step of the reaction, and it looks like it is. I'm just going to redraw these right here so they're easier to see. H, H. So this pink oxygen has too many hydrogens on it. We are going to remove one of them, and it looks like that's exactly what happens in this step in the box. Going from the top to the bottom in this box here, it looks like we are simply removing one of the hydrogens from that pink oxygen. So let's go ahead and do a proton transfer and remove one of those hydrogens. Let's take the lone pair on this water, and let's take that hydrogen, leave behind its lone pair, Whoops, let me do it in blue. Okay, let's take that hydrogen, leave behind its electrons as a lone pair, and that's going to give us the neutral oxygen below. There's a proton transfer. Okay, now what happens in this step, going from right to left? Okay, so we've gone, it's sort of a zigzag here. So we're going straight across like this, and then down, and then to the left, and then to the product. Okay, so make sure you follow that. So now we're going from this that I just circled, we're going to the left to get this. So what happens going from the right to the left here? Well, again, it looks like we are protonating that carbonyl on the right now. This right-hand carbonyl is neutral here. On the left, it becomes protonated. So what happens? Well, it must grab a proton. So we do another proton transfer set of arrows, showing that this is grabbing a proton and becoming protonated. Okay, that gives us this protonated carbonyl. Now what happens going from this molecule over to this molecule on the left? Now this is where it might get a little tricky, but clearly we are forming a ring system. So what is happening here? Well, let me draw these lone pairs in. One of these oxygens is attacking the carbonyl to make a ring system. We're closing this ring system, okay? This would be called an intramolecular reaction. I'll write that up top here. Intramolecular. This would be an intramolecular nucleophilic attack. I'll actually put it right here above the arrow. Intramolecular nucleophilic attack. Intra, meaning in the same molecule, we have a nucleophilic attack. Now, which oxygen is attacking? Well, it turns out it doesn't matter. Okay, they're both 6 away. If you count up 1, 2, 3, 4, 5, 6 atoms away from the base of the carbonyl. So it doesn't matter which one you draw. I'm just going to take this oxygen's lone pair because it's the closest. I'm going to draw a curved arrow. Let me do blue. Take a curved arrow from one of the lone pairs and attack the base of the carbonyl. Remember, when we do that, we kick up the pi bond, to be a lone pair. And so what we're doing with these arrows is we are indicating that this oxygen here, this oxygen, I'll keep it in green because it was in green before. That green oxygen is attacking the carbonyl on the other side of the molecule to make a bond to it. So it's a nucleophilic attack, making a bond. When it does that, it kicks up the pi bond to be a lone pair. And so we've successfully formed a 6-membered ring where that green oxygen is now part of that ring system. Okay. That green oxygen has a hydrogen attached to it still. And so we have to take it off. That's the final step. If you look at the final product, you'll see it does not have that hydrogen on it. So the final step is simply a proton transfer. Okay, let's draw H2O here. And let's draw a proton transfer to get rid of this hydrogen here. So we'll grab the hydrogen using one of the lone pairs on water, and we will leave behind the lone pairs. Okay, so we're grabbing the hydrogen. This is a proton transfer. We're taking that hydrogen away, and we're leaving behind its electrons. Okay, because we want to get rid of it. If we look at the product down here on the bottom, it does not have that hydrogen, so we want to get rid of it. So right now, we're not really focused on why things happen. What we're focused on with these problems is simply drawing the proper arrows to show what's happening, okay? So don't worry too much about right now. Don't worry too much about why things are happening. Just focus on drawing the proper arrows, okay? As we discuss the next few chapters, we'll talk about what makes a good leaving group, what makes a good nucleophile, etc. But for right now, it's really focused on drawing the proper arrows, okay? So again, look through this problem. It looks like a lot, but work through each step of the problem and make sure you understand the arrow pushing. Follow the electrons, follow the protons, and make sure everything makes sense, okay? Okay, for the final problem here, we are going to look once again at a mechanism, and we are going to simply draw the mechanistic arrows represented by each step. Okay, so we're shown everything that happens. We're shown all the reagents. We're shown each step, each product. All we have to do here is fill in the mechanistic arrows, okay? And we'll discuss each step. So looking at the first step, we can see if we compare the starting material to the next product, all we're doing is we're adding a hydrogen, adding a proton to the nitrogen. So this would be a proton transfer step. Let's show the proton transfer here by drawing a curved arrow from the nitrogen's lone pair to this hydrogen. It could be any of the hydrogens on this H3O+. Okay, an arrow to a hydrogen, and then an arrow showing that the electrons in that OH bond are being left behind. We're just taking the hydrogen, just taking the protons, not the electrons. Okay, so this would be a proton transfer. The next step here, if we consider this circled molecule to this circled molecule, what happens between the two? What's different about them? Well, it looks like we are adding an OH2, an H2O, a water molecule. It looks like a water molecule is being added here, okay? Now, this is where we will see, this is something that's slightly new here, but we can compare this C double bond N to a C double bond O. Okay, let me draw up actually on the bottom here. Now we know a C double bond O is partially negative up top, partially positive down here, and we can get nucleophilic attack on the carbonyl. Now the CN is very similar, okay, especially when that nitrogen is positively charged like that. The C double bond N and the N is positive like that. It's very similar to the C double bond O, where we can get nucleophilic attack, and then the pi bond gets kicked up as a lone pair. Okay, so it's very similar to the C double bond O. So let's look and see. We have water here. This water molecule is adding to which carbon? It's this blue carbon. See that blue carbon there? That water molecule is being added to that blue carbon. So let's draw a nucleophilic attack from the electrons on oxygen, attacking that carbon to make a bond to it. Now we have to kick up that pi bond because that blue carbon already has 4 bonds. So we have to kick up this pi bond to be a lone pair on nitrogen. Okay, so let me draw that over here also. We see a lone pair on nitrogen there. Okay, so this is a nucleophilic attack. The oxygen is attacking that. Let's actually type this out. Proton transfer is step 1, and then nucleophilic attack is step 2. We have a nucleophilic attack of water. Okay. Now step 3, going from here down to here. Okay. Going from this circle down to this circle. What's different? Well, we're removing one of the hydrogens, one of the protons from oxygen. Okay, so we're removing one of the protons from oxygen. So this would be another proton transfer. This is a proton transfer. Let's show the mechanistic arrows for this. Let's take a lone pair on water and steal away one of those hydrogens, leave behind its electrons as a lone pair, and this gives us the product on the bottom left. Okay, now comparing the bottom left to the next molecule in the sequence, what's different? Well, the nitrogen is gaining a proton. So again, this is going to be a proton transfer. And let's draw the mechanism for that proton transfer. We're going to take the lone pair on nitrogen, and we're going to grab a hydrogen with it. Let's take this one. Leave behind the OH bond as a lone pair. And that is going to give that nitrogen an extra proton. There's the proton transfer. Now, this step is probably the trickiest step for a newcomer to look at. But take a look here and try to figure out what's happening. I would recommend pausing the video and trying to figure out exactly what's going on between this box here and the next step, which is this box here. We're not given any reagents, so there's no reagents for this, okay? But what's happening between these two boxes? So what's happening here is essentially we're getting the loss of a leaving group. I'm going to put it in quotes. We're kicking out a leaving group, but I'm putting it in quotes because the leaving group is still attached to the molecule. We're sort of just kicking off this leaving group here. Let's draw some arrows. We see that we have a C double bond O. Okay, so if we have a C double bond O, that means these electrons are coming down to form that pi bond again. And we're kicking out this leaving group in quotes, which is this positively charged nitrogen. We're kicking it off, but it's still connected on the lower part of the molecule here. It's still connected there. So it's actually not falling off the molecule. It's just breaking apart at that section. Okay, so this is loss of a leaving group with internal assistance from this oxygen. One of the lone pairs on this oxygen is kicking off with internal assistance. It's coming down to form a pi bond and kick off this nitrogen. Okay, when it does that, we're given this molecule off to the right, where the oxygen is positive, the nitrogen is now neutral. And if we compare this to the final product, the only difference is this proton. So let's draw the proton transfer step to finish off this mechanism. Let's take the proton here, drop those electrons off on the oxygen to complete the proton transfer step, and that gives us our final product. Okay. So this is quite an advanced mechanism for introductory organic chemistry. Again, we're just focused on the arrows. Now in future lectures, hopefully we will be able to do this mechanism with only given the starting material and the reagents. Hopefully we can work through the entire thing. But again, what we're focused on here is the movement of these electrons, showing the curved arrows and understanding what's happening, okay? Okay, that's everything for workshop 7. If the mechanisms aren't making much sense to you, we are going to get a lot more practice in the next few chapters. So just hang on until then. Okay, see you in the next lecture.